All right. So here we go. We got, let me call this up. There we go. Whoops. All right, here we go. In the X direction, the spacecraft has an initial velocity component of 22 meters per second, okay? And an acceleration of 24 meters per second squared. Ooh, that's like 2.5 Gs. That's pulling a lot of acceleration. In the Y direction, in the analogous quantities are 14 meters per second in the Y direction and acceleration of 12 meters per second squared. At a time, 7 seconds, find the X distance that it traveled and the Vx distance and the Y distance, and then the final velocity of the spacecraft. Okay, this is just your vector. This is just your vector fun that you did before. Break it down into its two components. I'll show you how that works. Let me write down the initial things here. So we're going to have V naught x is equal to 24 meters per second squared. I'll let you watch what I'm writing down. Oh, now hold on, and then V naught y is 14 meters per second. Wait, oh, 22, and the acceleration x direction is 24 meters per second squared. So I'm getting this straight. And 14 and a y is 12 meters per second squared. Okay, then we're going to let it go for t equals 7 seconds. And the 7 seconds is going to act on both of them. All right, so here we go. Now take a look. Talk to me, Ladybug. It's going to spin. Sorry about these delays. Come on now. Coming to Papa. There we go. All right, now let's open this sucker up. Now look. You work the problem basically in two columns. And t equals 7 seconds is in both of them because it's the same spacecraft. So we want to find out how far it went in 7. Now it's accelerating. So we want to find out how far it went in 7 seconds in the x direction, going this way. And it's also lifting up going this way. And then when we're all done, we'll take those two components and the final velocity, the overall final velocity will be the square root of v naught v final x squared and v plus v final y squared. And then the direction of it will be theta equals the inverse tangent of v final y over v final x. And the distance, the overall displacement of it, r, will equal the resultant of x final squared plus x y squared, and then the distance. That's where we're going. Okay? That's the goal. So you work your x's, you find this guy, then you find this guy, and then you'll work your y. Find this guy and this guy. Now, when we get to projectile motion, when we launch things here on Earth, the acceleration will always be here, and it'll be negative 9.8, and there is no acceleration here, so this will never change. Okay? All right. And I'll do that video for you on Tuesday. So we'll do those together at class on Thursday. So, but let's just get this one done first. All right, so here we go. We want to find out what's its velocity. So v final in the x direction would be 22 meters per second. That's our v naught, plus the acceleration 24 times 7. This is times at. I swear to God, I had my calculator out here somewhere. Here it is. Still in my bag. All right. So we got 22 plus 24 times 7. 190 meters per second. Thing's flying. And then the distance that it went, x final, is equal to, oh, this should have been y final over here. Sorry. All right, x final will be x naught plus v naught x times t plus 1/2 ax t squared. We'll just plug in the numbers. This becomes pretty easy. 0 plus 22 times 7 plus 1/2 of 24. Well, I'll put in the 1/2. 24 times 7 squared. So it'll be 22 times 7 plus 0.5 times 24 times 7 squared. Boom. 742 meters. Let's do the same thing on the y direction. V naught y, v final y is equal to v naught y plus at. So this equals 14 plus 12 times 7. (98) meters per second. That's going up, okay? And then y final is equal to 0 plus 14 times 7 plus 1/2 of 12 times 7 squared. And so y final times 7 plus 0.5 times 12 times 7 squared, 392 meters. Okay, so our final velocity vector is equal to the square root of 190 squared plus 98 squared plus 98 squared. Lets you see what I'm doing. Equals this. Take the square root of that. 2.213 meters per second. That's how fast it's going. In a direction, the velocity vector is in a direction of the inverse tangent of y, 98 over 190. (27 degrees, 27.3 degrees above the x-axis, positive x-axis. And then the displacement, the overall displacement, r, is equal to the square root of 742 squared plus 398 squared, which is equal to 842 meters. And the direction, once again, the inverse tangent of 398 over 742. I didn't check to see if I was doing this correctly. I just assumed I knew what the hell I was doing. 28.2 meters. So notice it's a little bit different than the velocity vector because it's going to be a little bit different. All right. It's pretty close. All right, so let's see what they say. Okay. Make a drawing. Oh, I didn't make a drawing. And then write down the values that are given for any of the 5 kinematic variables association with. So I always have my x column and y column, which is what they said. Verify that it contains values for at least 3 of the kinematic variables. Do this for x and y. Select the appropriate equation. When the motion is divided into segments, remember that the final velocity of one segment is the initial velocity of the next. Keep in mind there may be 2 possible answers to a kinematics problem. Okay, I think they might mean there's two possible ways, two possible answers. Oh, yes, because if you're using that x squared thing, I hate this when my phone starts going off. All right, so here's all the stuff that we did. Example, moving spacecraft. Found all this. So far, so good. Yep, yep. That's what we did. Yep. So there it is. Now, we get to projectile motion, which I will save. This has been enough for one day, which I will save for Tuesday. Okay, we'll do projectile motion. And then a real good thing is the relative velocity part, which is the end of the chapter. All right, so this will cover the first few problems that I'm going to give you to do. That'll be due probably a week from Tuesday. And then the second set will be the projectile motion. So out here,